Okay, last time we started with indexing, how to integrate indexing into our database store, and that's where we recap a little bit and continue today, because indexing has a huge importance on the performance of a database system. So far, whenever we wanted to retrieve data, we looked at all data and applied a filter. We checked, okay, does this data item qualify under the filter? So in relational algebra, that means we look at the relation, then there's a filter condition, yeah, and we inspect each and every tuple on our world, each and every object, whether it qualifies under a certain condition. And that's a no-go for performance reasons. So we need to integrate data structures. We need to integrate lookup structures. Database people don't say data structures, they say indexes. So that's why I'm coining it indexes in this lecture as well. So we looked at this diagram here last time. Yeah, and basically we extended the store. So previously it was like that. So we had the key value store and the MVCC store. And then we extended that to wrap again the MVCC store to be an indexed MVCC store. And we look at that, what that means and what that entails, because a couple of new methods will be added. But inside that indexed MVCC store, we will have index structures. Index structures allowing us to look up a specific key, yeah, without having to scan all of the existing key value pairs in our store. Yeah, and then we talked about, okay, there's all kinds of indexes everywhere. There's indexes underneath. The store itself is an index, and the store has indexes, and all of these things. And basically then we started into looking this problem, okay, now if I keep indexes here, yeah, so I have an index allowing me to do a quick lookup for a specific attribute value, or give me all objects that have an attribute A, where the attribute value is set to 42, then I have to make sure that these indexes are kept in sync with the other data stored in the store. So if I update anything in the store, so whether I look up the store with a scanning all the objects, or whether I look up the index, that must at all times return the same result. That's the invariant that holds here. Yeah? If you look a little bit at that, how that works in the code today. Yeah, and we talked about here, of course, then there's this is called index maintenance. Yes, you have to maintain the indexes, meaning whenever there's a delete, insert, or update, you have to keep track of those indexes. And now we're in a special situation here, that is, we have a version store. So far we don't remove anything from the store. Yeah, we keep the committed versions. We keep on appending, the lists keep on growing and growing, and so forth and so forth. And the way how I implemented indexes here is one design choice. You could make others. My design choice in the store is to say, okay, I want to have a superset of the object IDs that have an element qualifying. Yeah, in other words, if you have different versions in a committed list and one of those versions qualifies under a predicate, I will return that entire list. Yeah, so basically the index gives me the object IDs where the committed list or the work in progress list may have a qualifying tuple. Yeah? And that means that you still have to check which is the right version. What is the version to return for the transaction that's querying the index? Yeah? That's the same thing as with standard snapshot retrieval we had in the unindexed store. Yeah? You'll see in the implementation in a moment what that means. Yeah? Okay. Yeah, again, I have this is a UML diagram I showed from the non-indexed store, now extended that a little bit. Personally, I don't find these diagrams too helpful, actually. Not sure. I think the visualization here that PyCharm offers is not great, and that's really one of the few things that the PyCharm people should fix. So I'd rather show that to you in the code. So let's look at the code a little bit. So basically what I changed here is that you now have an indexed transactional key value store extending the existing transactional key value store. That's the MVCC store we talked about. I just renamed it at some point. And then there's a new interface that's being weaved in, so to say, or mixed in. But it's not just a mix in of one method, it's multiple methods. So this is an extension of the asset store we had before. There's an asset store interface allowing me to begin transaction, commit transaction, abort, update, delete objects, and so forth. And now I extend this interface, allowing me to create indexes, to drop indexes, and get suitable indexes. So create index means the user sends, please create this index structure and use it for further query processing. Yeah? And the create index, here the idea is, okay, you give it a name, you say it's an attribute. So an attribute that should somehow exist for your object. Again, recall we have a very generic key value store here. So it's not relational. Yeah? It doesn't have to be relational, let's phrase like that. But if it has some sort of attribute, if the object has an attribute that matches to the attribute specified here in the index, then the attribute value will be taken and maintained by the index. You see that how that works in a moment again. Yeah? Just recall this is not purely relational, can be anything here. Then there's an operator to be supported. For the moment, that will be equality only. So you will see I pass an equality symbol, but you could have indexes that are smaller equal or something like that, and index all kinds of stuff. For the moment, it's just about equality to simplify your life. Drop index removes the index from the index store. And then later on, once we talk about query optimization, we will have a method get suitable index. Yeah? So eventually the query optimizer has to make a decision whether to use the index or not use the index. And basically the query optimizer has to get a list of possible access paths, yeah? So possible options to retrieve data. So far we only have one option to retrieve data from the store, that is scan everything and filter the stuff. Now we add more possibilities. Yeah? Now if you want to have everything where a equals 42 and there's an index, well, you can also directly use the index without scanning the stuff. That's a different access path, a different way to access the data. And that's what the query optimizer needs to know about. So you could ask yourself, why not use the index? So if you have a where clause, a equals 42, and there is an index, why should you still offer a scan to the query optimizer? Yeah, so we're in a situation, we have a query, a equals 42, and we have two options. You scan everything. Scanning means for each object, ID, comma, object in my key value store, yeah, scan the entire store, or use the index. I make a triangle, that's a widely used symbol for indexes typically. You see that very often in these. So we have two different access paths. Two access paths. And there could be more access paths. But obviously the index is always faster than the scan. So why even offer such a method here? Why not directly use the index at all times? Any idea? Mm-hmm. Again?
Maybe this data haven't been indexed yet.
Yeah, sure. You can. So the method will work as follows. So if you have, you pass a condition, there was a method here. Yeah, you would pass attribute name is a, an operator is the equal symbol. Yeah, and then the indexed store should return, okay, what are the possible access paths for this specific attribute operator combination? And if there's no such index, this method won't return this. Yeah, so the fallback is always scanning. That will always be returned here. But if there is a suitable index, it will in addition return the index. That's the idea of this method. But then why return the scan if there's an index? Yeah?
So the signature of the function accepts a single attribute of the object.
Yeah.
So in real cases, we could have like a composite.
Yes, of course. It's a simplification, very good point. Yeah, so you could have a condition. In the general case, it's a predicate, yeah, an arbitrary predicate, a conjunct, disjunct of stuff, yeah. That would be the more generic function. I simplified it here a little bit to say, okay, there's just one attribute. One attribute and one operator, and that's it, and that's what the store supports. But you could have indexes on composite keys. So an index where the key is not only one attribute, but the key is A, B. Yeah? A composed key in database lingo. That's true, yeah? But that's not an answer to my question. So assume we're in this world. We have just one condition. Why would I return the scan? Any idea? This problem occurs when you have indexes that are backed by external storage. And they really can enter a world that, depending on how much data you retrieve, let's say this is the time it takes to retrieve data from a certain index. Let's assume this is a scan. Yeah, this is the time to scan data. And on the x-axis, I depict the selectivity. So how much data is returned from the underlying relation. So you would say from 0 to 1, 1 meaning the entire table is retrieved. All tuples, yeah, let's stick to the relational model for a moment. So all tuples from the table are retrieved means 1. No tuples are retrieved, so basically no tuple qualifies under the filter. 0 is retrieved, and that's something in the middle. This is called the selectivity. Yeah? We had that in the undergrad lecture several times, actually. And now the problem with some indexes, so we would expect whatever you do, the index is something like this. Yes, the index performance is always better than the scan. That's what you would expect. However, there are index structures that more look like this. And they really, hey, where are you going? And that's a problem, because if you make a bad choice here, you might end up with an index access plan that you believe is better, but in fact is like 5 times slower. Yeah, and that may happen if the index is backed by bad storage medium like hard disks. Spinning disks with these platters, they can really ruin your life in a database system. With modern hardware, it's not so much of a big problem anymore. You more run into this more in high-end scenarios, high-performance computing. But in older systems, or it doesn't have to be an old system, it can be a new system. But for instance, we have a system here that runs on hard disks, on platters. Then you can actually run into this problem. And then the job of the database system is to make the right choice. Yeah? You could say there's some database systems that say, I don't care about indexes at all. I don't do that. There are systems doing that. I scan at all times. But what I gain is a robust execution time. Okay, this execution time is not so great, but I cannot fall off the cliff. Yeah? I can't run into this situation if you always choose the scan. Yeah? But of course, that's not a wise choice. A better choice would be to say, so if you don't have this index, you always want to have the skyline. Yeah? Basically this. Yeah? So until you're here, you should pick the index, and starting from there, you should pick the scan. And that is what database systems actually do. That's what the query optimizer does for you. You don't have to worry about that. The query optimizer will try to do exactly that. So it will try to estimate, under this condition, what is the selectivity given my statistics, how many tuples will be selected. With that, it will estimate the selectivity, and then it might estimate, okay, I'm here, and then it will run the scan rather than the index. Yeah? And these estimates by the database system can go terribly wrong. Yeah? We will look at that again in the context of query optimization. But here in this method, the reason why this is returned is exactly giving the choice, giving the option in the case where the index may have a performance that's worse than the scan. Yeah? If this index always dominates the scan, you don't have to return the scan. So if you can deduce from your index implementation that it will always outperform this other scan, then you can return it, right? Then you don't have to return the scan, right? Now I'm entering the trick question space, maybe. Sorry. So what I just said is, okay, if you know that this cannot happen, your index implementation is such that it's not backed by shitty memory. Maybe it's a Python dictionary or something like that. And you know, whatever you do, whatever you specify, this is not going to happen. So this is always faster. Yeah? You're always in this space. Yeah, you're always like, boom. Would you still return the scan? Yeah? Yeah, okay. No, assuming that for this specific attribute you're looking up, the index exists. Yeah? Again, in this situation, yeah, you know that your whatever Python dictionary will dramatically outperform the scan. Yeah?
I mean, if I understand the architecture correctly of the software, I would still return it because this is the query optimizer which should take into account optimization, and this part of the code is supposed to just return all the suitable methods.
Yeah, that's a software engineering argument you could make. So what he's saying is basically the signature is like that. The store should be dumb. The store shouldn't preempt any decision. It should say, hey, those are my access methods. You do whatever you want with that. That's not my job. That's a very good answer, actually. Yeah. If he loosen that a little bit and say, okay, now let's give this method some smartness. Let's allow it to say, okay, I have 5 different access methods, and I know these 2 will never win, never. Yeah, so why would I return them anyway? Yeah, maybe that's a bit hard to see probably, but it could still make sense to have scans actually, and the difference will be certain properties of the data. It could be that the scan or the output of the scan has a certain property like sortedness. Assume that the index, maybe you look up many elements. Maybe you look like half of the, let's make a new graph. So let's assume this is our scan. And let's assume the Python dictionary is like this. So it's clear, locally, the index lookup, yeah, this is a Python dictionary, it's the same graph, selectivity. This is time again. So let's assume we're somewhere in this space, so it's clear. Yeah, it's clear anyway. Whatever the selectivity, locally meaning the index lookup alone. If you just look up the index lookup, yeah, that's cheaper. That's true. But it could be, for instance, that the scan returns the element sorted by a certain attribute, maybe sorted by this attribute or sorted by another attribute, which you may exploit later on. Yeah, it's a similar argument. So it's a kind of break. I mean, if you ever had dynamic programming, that's kind of where dynamic programming breaks or has to be extended, because if you leave away a scan, yeah, then you do a local optimization, but you don't know how this stuff is used further on in the query optimizer. So it might globally yield to a plan that still uses a scan, even though locally the index would be faster. Yeah, so it's local versus global optimization, and therefore this method should simply dumply return all the available indexes. Okay, where was I? Yeah, so this is the extension of that interface, so the indexed asset store, and now we can look a little bit at the implementation of that. So I think we started looking at that last time already, and yeah, maybe I just wanted to say, because someone approached us, I think I explained it very clearly in the beginning of the lecture. So this lecture is driven by the implementation. So we look at a lot of code. Yeah? I said that multiple times, and that means that not all of the concepts are fully spelled out on the slides. That's the core idea of this lecture, actually. Yeah? So I try to summarize, I try to present core concepts on the slides, but then the difference to previous lectures, in previous lectures we had a lot of pseudocode on the slides, which was actually partially wrong, and no one really complained about that. And now it doesn't make sense to put pseudocode anymore on any slide. It really doesn't make sense, yeah? Because the code is there, and Python is so close to pseudocode. Yeah, so we actually now start putting Python code in our papers. Previously it was pseudocode, and you always made a mistake. It was really, really annoying. And now what we do is, we have a proof of concept, we write it like here in the lecture, we write it in Python, and we write tests and make sure it's correct, and then we put it to the paper. And then we are much more confident that the stuff is correct. And that's something I would highly recommend. Yeah? Put Python code as a replacement for pseudocode. Yeah? I think pseudocode is mostly, sometimes also not so readable, and often it's wrong. Yeah? And for this lecture, this means that really is, we expect you not only to understand the slides, but also have an idea about the core concepts and algorithms and design of these things. Of course, not to every little detail, but for instance, for today, you should understand that, okay, index maintenance, yeah, that means that I have to, through polymorphism, I have to do some extra stuff in my update object methods to maintain the indexes. Yeah? How that looks in detail, sure, we can debate that, but you should have the idea, okay, I maintain indexes, I have to be careful when updating stuff, and there are, I remember vaguely some trick. Yeah? So in the exam, we won't ask for Python code, and we won't ask for design, and we don't ask you to scribble down UML diagrams, but we might have questions like, okay, assume you wanted to do a store like this, what are the things you should care about, or where you should be careful? Or assume you have a query processing scenario like that. How would you solve that in pseudocode? Yeah? Pseudocode can have syntactic errors even here and there. If you understand, like you got the idea, everything is fine. Yeah? Just as a clarification. Yeah? So this lecture is really not only about slides. This is really integrating more what we had as a very separate project before is now more integrated. Yeah? Okay, that's what I wanted to say about that one. Yeah, and I think, so for create indexes, for the create index method now in the store, what you need to do, of course, you should make sure that the name is not already there. The operator must be equal. Other operators are not supported yet, but you should, of course, in a real implementation support other operators. And then I add metadata to what's called the catalog. In a database system, the catalog keeps metadata. We didn't need that so far because I never created a table. But if you create a table in a database system, you should keep track, okay, what the heck is the name of the table? What are the attributes and what are their types? That meta information, that metadata is kept in what's called a catalog in a database system. Every database system has such a catalog. And the major differentiator, we touched about that in the assignments actually, is, okay, is that metadata catalog transactional or not? So can I change a table? Can I create a table as part of a transaction? Does it fulfill the asset properties? Unfortunately, some database systems decided to not make transactional, but it would be better to have a transactional. Here I have a dictionary. So what does it mean for transactional properties? So this is basically, if you go to that, I think I have it here now in the constructor. I initialize, that's a breakpoint. So in the constructor, I create these two dictionaries. Yeah, so those are the indexes by name and the indexes by properties. Properties meaning simply that's the attribute name and the operator being supported by that specific index. That's just an extra type I created for that. But basically, whenever there is an index, I will now make appropriate entries in those dictionaries. And if I drop an index, okay, I remove those entries from those dictionaries. That's the idea. So keep track of the indexes that are available in the store. So what does it mean for the asset properties of our store? I think we had an assignment in a question about that in the current assignment. Yeah, what does it mean? So I keep information in something that's not managed by the store. So the store does all of this validation stuff, MVCC, snapshot, read, comparison, checkpointing, checksums, whatever. We talked about that at length. But this data is completely managed outside all of this. So if there's a conflict between what I do with the indexes and what I do with the rest of the data managed under MVCC, I won't see this stuff. Yeah, that's not good. So it would be better to here integrate this data into the store somehow. Yeah? ideally by rerouting these dictionaries to the existing storage mechanisms, by routing it to the underlying MVCC store. If I do that, I'm fine. I get transactional properties for free. But if I do it like this, anything may happen. So you have to be careful about that. Okay. So create index. So here we do these entries into these dictionaries. I also create an index structure. That's a Python dictionary. I simplified that over last week's lecture a little bit. Maybe we briefly look into that. Last lecture, we had these 2 Python dictionary implementations. Now we only have one that also allows for duplicates. And we made life a bit easier, in particular for the get method. Now the get method doesn't return a value, but it returns an iterator of values. So you can directly call get in a loop for I in get tralalala and then iterate over the values, which is much, much easier to handle in code. To write an iterator, also called a generator function, or a generator in Python, you just call yield. And the magic Python does is, so if you have a loop that returns multiple entries here, for each element in self-index key, so this internal Python dictionary maps to a list of values. So for every key, there may be a list of values, which means yield will be called multiple times. But all the handling where I am in the list and what to return is handled by Python. That's super cool. Yeah? So been doing that in Java at least 10 years ago. You had to unroll the loop manually, but here you just say yield, and if you call the iterator again, it will just continue with the loop in the right position, which is super cool. That makes your code so much easier to read. So if you never use generators, take a look in the Python documentation. That's super cool and super useful. Right. That's basically all we changed. So we have this Python dictionary now. And in the create method we create an index, Python dictionary wrapped by our index API. We also add it to the catalog here. And then, okay, we have to now bulk load the index. So that's a term meaning, okay, we have to make sure that the index reflects the current state of the store. And that's what I do here, again, through a very inefficient method. Because here I say, okay, whatever items I have in a store, I scan over those items, I loop over those items. I get the entry from that from that loop. So basically the object ID and the version list mapped to. And that is key value store entry. If you recall, that's this internal, maybe you can also go there, why not? That's basically this one where we have the start validity, the value, and where that was deleted. Yeah, that's a version entry. And then basically I add that version entry to the index. That's what we do here. And I do that through a separate method called index object. That happens here. So basically the core idea of this is, okay, now I have some data and I put it into my index. I throw it into my index here. Yeah, and then the index, what it does is, so for each incoming object, so here I specify the object ID and the object to be indexed. I check whether that object even has an attribute. Yeah, so if I specified the index to be indexed on attribute A, now I check whether this Python object has an attribute. And only then I even consider it in the index, otherwise I don't have to index it. In the relational store, you don't have the problem, because there, if you create an index on a specific relation, it's guaranteed that, yeah, if it's in this schema, then all tuples in that table have the attribute anyway, so you don't have to do this check. But in the key value store, you have to do the check. Yeah, then you get the attribute value from the object, and then you put it into the index through the existing put method. That's what happens here. Okay. So here we go. Basically, once you do that, you have the index maintained. Yeah? The same happens for, or similar thing, much easier though, happens for drop index. Here you basically just delete the metadata. You could also delete the index here. I think we briefly touched upon that last time. You should also delete the index. Here it's just deleting the metadata. Okay, and the pitfall that you have to be really careful about, and that's why we now look into the update methods. This was update object. So this is an update object method that's extending through polymorphism the method from the superclass. Yeah? The superclass already, the standard store without indexes, had that method as well, but now we have to do some extra stuff. We have to maintain the indexes. Yeah? So you will see at some point we are calling this method, the update object method, but before that we we secure the work in progress entry if it exists. That's the only pitfall here that you have to be careful about, because I mean it's all about putting more stuff to the index, because in the version store we just keep on adding material, we just keep on adding new versions, so that's fine. Yeah? But there's this one situation where one transaction overwrites its own work in progress entry. It sends multiple updates. Every update creates a new work in progress entry. So when you create a work in progress entry, it will be added to the index. But now, if you update the same object ID again, you must de-index the old work in progress entry. Otherwise, you would be showing something that's not available in the store. That's the only situation where you actually de-index. And that is wrapped here in this method called maintain index. So maintain index, you can pass something that should be indexed, should be added to the index, and something that should be removed. Yeah? So only if this existing work in progress entry is not none, then you remove it from the index. Yeah? And that's basically the idea. And getting back to my comments before, that's in understanding you should have and take away from the lecture and for the exam. Yeah? So the idea, okay, when do you have to put something into the index? When do you have to be careful? Work in progress entry. But the main thing you need to understand here is, okay, whatever you have in your committed list, you should put it into the indexes. And then you're good to go. Yeah, and the similar thing then happens for delete objects. So for delete objects, again, you have to be careful. Okay, maybe I created a work in progress entry before, same trick here. Then you call super for delete. And then there's no object to index, because you just create the marker in the committed list that this object ID's object was deleted. Yeah? Mm-hmm.
I may have missed in the index and the get indexes.
Index and indexes, yeah.
Are we passing the transaction ID? Because the result of an index will be different depending on which time
yes.
do we...
Yes. The indexes I create here, the idea of these indexes are that you map. It's also called a filter index. So it's not an index in the traditional sense you might have learned about in algorithms and data structures. You look up the index with key 42, and the index gives you everything that qualifies. And there's no post filtering. Whatever is returned, yeah, that's something I should look at. A filter index is something that computes the superset of the actual result. It's a compromise in the way that it gives me those object IDs that might have a version that qualify under the predicate. Yeah? So that's maybe one part of the explanation. So the indexes are implemented like that. And hopefully you didn't get it wrong. But that's the idea. Yeah? So the other design decision could have been to index each version individually and just give me the versions that actually qualify. That's also a possible design choice, but I took the design choice here now. Again, it's kind of, one motivation was also to make it simple. Why should I worry about individual versions? Because, I mean, what do I lose? In practice, those committed lists will be relatively, will not be so long, because in the real implementation, you will prune anyway and just keep the stuff that's being used by any transaction. So those lists will be small. So why spend the effort in implementing, indexing individual objects, right?
Then the possible downside would be, for example, have a table that stores some count of something.
Store some?
Count.
Yeah.
That we always initialize by 0.
Yeah.
And we would be like our vacuum process would be like
yes.
super slow.
Yes.
But index of something is lower than something.
Yes, exactly. That's exactly the trade-off. Yeah? The trade-off here would be, so you have a counter that's incremented like crazy by many, many transactions. You get long lists. Yeah, then you better have a vacuum process that prunes the list like crazy. Otherwise, my indexes will have a problem. Yeah? On the other hand, maintaining you still have to do anyway. So you add a new version, maintenance wouldn't change. I mean, if you maintained your indexes to just show the currently available attribute values, in that approach, where the index really points only to the qualifying elements, that also means that whenever anyone changes a count, you have to remove it from the index. That's the price you pay there. Yeah? And then it depends. Good, very good. Okay, where was I? Okay, so on that level, that's the understanding you should have. And then basically, if you look into those methods, I recommend, of course, to look into that. Again, we write tons of documentation, as always. Then basically, what you do is you have to loop over all existing indexes. Yeah? Then you check, do you have to index something? Do you have to de-index something? And then basically you have to call this index object for that particular index on that attribute, and then you add it to the index, and so forth and so forth. Yeah? So it's, the more indexes you have, the higher the costs for maintenance. Yeah, you see that's this loop, yeah? And that's actually can be quite a killer. That means the more updates you're sending to the store, the more expensive the update becomes, not because the update in the store is expensive, but you have so many indexes to maintain, right? The vice versa, the fewer the updates, the less you should worry about index maintenance. If there's only one update per day, I don't care. You can create many, many indexes. Yeah? And that leads to another very important trade-off in databases. And that is basically, so if you characterize your workload, if you characterize the number of queries that are coming into your system, you could say, okay, this is read-only, and this is write-only. Yeah, just write, just update, inserts, and deletes. This is just reading, just select tra-la-la-la-la from whatever. Yeah, and of course, the real workload is somehow in between, but that means that the costs for updates under a certain number of indexes will vary. Yeah? If you have many indexes, the update cost, I mean, there's no updates here, yeah? But the update costs, of course, maybe follow a relationship, something like that. Yeah? The more writes you have, the higher the costs for no, this is bullshit, right? What I'm trying to, maybe, give me another attempt. What am I trying to say? First, label your x-axis. First, label the x-axis and then draw the line. That helps a lot. Okay. So what do I put on the x-axis? Costs for updates. No, it doesn't make sense. Now let's make it another. Let's make a number of indexes. That's what I was trying to say. So the number of indexes a system could have like that is typically something like this. Yeah. I mean, you could change. Depends on how much you want to pay for a certain update. Yeah. But you will see that another way we had that term before. It's on analytical systems. called OLAP, online analytical processing, they're mostly read-only. But transactional systems are more on this side. Yeah? They're not strictly write-only, they're more in the middle, OLTP. And then there's streaming systems that are actually can be considered write-only, streaming. Yeah? And then depending on where you are, where your workload sits, it basically means that in a read-only scenario, you can create as many indexes as you want. I don't care. It doesn't matter because I don't pay an extra price for index maintenance. If you never change your data, you can create as many indexes as you wish. Yeah, in particular, if you have a relation like that, A1, those are the attributes, A2, blah, 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 and then, so we're entering SAP space, kind of. That's what they use in these systems. And then, you have your rows here, row 1, row 2, and tra-la-la-la, and you have these huge tuples. So how would you index this stuff? Yeah, because if you have so many attributes and your method only allows you to create an index on one particular attribute, okay, yeah, in the worst case, you have to create an index for each and every attribute because there could be an A765 attribute equals 47. How do you look up this stuff? If there's no index, you can only scan. Yeah? And that means that's an important trade-off to consider because if you assume you indexed all of these 1,000 columns and now an update comes in and then you enter in this loop, yeah, for each of the 1,000 indexes, you have to call the index and update the object. Yeah? That will totally bring down your update performance like crazy. It's not going to work. Yeah? And therefore, this is an important trade-off to consider. So, of course, as in many situations, indexes are a great idea, but there are limits to how many indexes you can create without sacrificing update performance. That's an important design decision in such a system. And for performance profiling, makes a lot of sense if you have at least a vague understanding where you are in this space. If it's am I read-only? If it's streaming, is it OLTP? Somewhere in the middle. So most systems sit somewhere here. Yeah, you have to. You could profile. Okay, what are the costs for updating anything in my system? Maybe index maintenance is in the way. If I have 100 indexes in my system, maybe you drop some of those, yeah, and optimize your performance, factoring in the number of indexes you create. Yeah, and you see it here directly in the code. Yeah? Basically, this is the cost. This is the price you pay for something like that. Okay, right. So maintain indexes, update object, delete object. Yeah, and what's important is we also have to override abort. I almost overlooked that. So we have create index, drop index, of course. We have get suitable indexes. You can directly get that from the catalog, of course, because we keep track of the attribute name and the operator being supported. We will revisit that when we enter a query optimization land. But the interesting thing is we also have to abort, override the abort transaction method. Yeah? So here the problem is that, again, the work, so why would I care? Because how I implemented it like here is like, okay, I also index the work in progress versions of the object IDs, yeah, when the transaction is running. Why is the transaction is running? I want to index everything because I want to be able to send a read objects call down and get everything, including my own modifications from within the same transaction. Yeah? So I don't say I just index the committed stuff. I say I index everything, including work in progress stuff. And that means if a transaction aborts, those work in progress entries will never be added to the committed list, but the work in progress entries were added to the index. So I have to remove them from the index, of course. And that's what happens here. Basically, again, here the write set helps, yeah, because that's the object IDs are modified. I get the work in progress entries and do a couple of asserts. But then at the end of the day, what I do is I de-index the stuff. I de-index all the work in progress entries ever created by this transaction which is aborted. Yeah? That's again a high level concept you should take away. And then of course I call the super method, yeah? But only afterwards here, because if I did it the other way around, what would happen? if I first called super, and it's always a question in these methods, you see it very often when using polymorphism, do I first call super and then do my extra stuff, or first do extra stuff and then super? Or we had just a case where super was in the middle, I did some stuff, then super, and then I did some stuff. Yeah? Why do I call it afterwards? Does anyone remember? Yeah?
Because the abort transaction already cleared work in progress.
Yes, abort transaction already removes everything, removes the work in progress entries in particular. So I wouldn't have a chance. Or would I maybe through the write set? I think I still keep the write set here. Actually, no, actually it would work, right? I think the write set is maintained, but the work in progress entries are a problem, right? Object ID in write set. No, here I get the entry. That's a problem. Yeah? That would be none. That would be removed. Yeah? So the abort method of the store gets rid of the work in progress entries. Recall that's a log. That's avoiding the write-write conflicts in the store. And if you abort a transaction in the store, you have to remove all the work in progress instances used by that transaction, which means set the work in progress to reference to none. And that happens in this call. Yeah? Oops. If you call this, whatever you do here, the entry will be none, so it doesn't make any sense. So you have to do it before. You have to de-index the stuff before and then call abort, and then the work in progress entries will be removed in the store, and then you're good to go. That's a pitfall you should be aware of. Otherwise, if you don't overwrite abort transaction, so these entries will still be there in the index, and that's not what you want to have. Yeah, again, I invite you to look at the tests a little bit. Let's do that a little bit. So we have this tests folder, and there's test indexing, and there is this indexing test with a couple of test methods. And yeah, what do you do to test an index? You put some stuff into the index, you get an instance of that dictionary in this scenario, and then you put some stuff there, some key value pairs, and then you send a couple of asserts. So unit test, it's always self dot, and then there's an assert, whatever method, could be assert equal, could be assert greater equal, tralalala. So basically, you materialize your expectations about the index. So you know, okay, if I use the index like that, it should behave like that. And this behavior is phrased as a test. So it feels like, I mean, there's this difference between testing and trying out. Yeah? When people say test, oh, I tested my software, it's not immediately clear what they mean. Some people mean, oh, I tried it out, I started it, yeah, it looks good. Yeah? The translation is now testing is unit test, and there's a high coverage of your tests. So that's the difference. So basically, when starting to write tests, you try out your things. Yeah? You basically debug through your structures, in this case, a Python dictionary, and reason about, does it make sense? Doesn't it make sense? Yeah? And while debugging, you could basically write that down as a test. Yeah? So debugging is a good start to write, yeah, that's what should happen. Or you see doing debugging, oh no, that's not going to fly, there's some bug here, and then you fix it, write it down in the test, and then you preserve that functionality. So a major function about unit tests is to avoid code rot. Code rot meaning your functionality rots, code rot. Yeah, decays. Yeah, you have some functionality X, you do a change, all of a sudden the functionality is not there anymore. And that's a major purpose of tests, to make sure whatever you change in your system, this expected behavior, this functionality is still there, even though you change it at some point. Yeah, you can also check for, here for instance, we query, we try to delete a key that doesn't exist anymore, we already deleted it here, and then you can check for key error exceptions and stuff like that. Yeah, I don't know. So here it's basically, this is testing the store, yeah, the index transactional store. So what do? I create an index. I create the same index again with the same name that should raise that exception that the index already exists. I check that certain properties are true. For instance, yeah, this catalog I'm using to keep the track of the number of indexes. Yeah, there should be one entry there. So this checks whether the index store actually keeps track of those indexes. I could also go deeper here and test and check whether the catalog entries are correct and so forth. I don't do it. I just check for the size. Then I get the index here. I check the keys that are available there. And then, of course, if I have a certain number of unique keys, that's what I'm doing here. Basically, I'm removing duplicates here. Yeah, then that number, the length of that must correspond to my expectation. Must correspond to the size, because the size here is actually the number of keys being mapped. It's not the number of key value mappings, but the number of keys being entered into the index. Then I drop the index. Check for conditions and create the index again, and so forth and so forth. Create a second index, of course, then I have two entries here. Yeah, and then these indexes must be maintained, and so forth and so forth. Yeah. And this is just checking index maintenance so far. Yeah. So we're not checking the reads. And then I also have to check it under commits. Yeah, what's going on under commits? Maybe you read through that back home. Yeah, and then I basically compare against the correct index entries. If that's what I expected, tra-la-la-la, is the index maintained, tra-la-la-la, and so forth. What happens if I commit? What happens if I abort a transaction? Of course, an ideal unit test should also handle the corner cases. So if you feel like, okay, that's particularly difficult, so you should write a test against that. You shouldn't blindly brute force tests. I mean, that's something to start with, writing unit tests, but always think about what you're testing. I mean, it's low-hanging fruit is actually to create a lot of data, create a lot of put operations, yeah, and just as statistical argument, yeah, maybe in 1,000 cases you don't see an error, but then when doing 1,001, then you see the error. Yeah? So it's a stress test for your code. I highly recommend doing that, but typically that leads to the trap that your unit tests should run through quickly. Yeah, if the tests get too slow and you keep on adding tests and they take like 10 minutes to execute, you don't want to do that. Because the idea of a test is really you change one line in your code or change two lines in your code, and then what you do is you hit the button and see, yeah, everything is fine. Yeah, I didn't break anything. But if you don't execute your tests frequently, like if you say, okay, I spent the entire morning, and now I execute the tests again. Oh, they don't work anymore. So at which point did I ruin this stuff? Good luck with that one. Yeah? It's not fun. Yeah? So I really should execute it often. Okay, so I invite you to look at that. Because to me, it's always like when I write tests, when you're able to write a test, you really understand the store. You really understand the technique you're testing. That's really, you're often tempted to say, yeah, I looked at the code, I tried it out. Hey, write a test. If you can write a test, and then the next level is, of course, there's a bug and you understand how to fix a bug. And that's not what we're expecting here in the lecture, but you should, to a certain degree, be able to write a unit test against our structures. Okay, yeah, there's already the next test for the next part of the lecture coming up, and that will be